Hello students, this is Argen Kokitaev and I'm continuing the discussion of law of large numbers and central limit theorem, which is a part of the module on probabilities and statistics, the refresher module. We covered the theory in the previous video. Let's see if right, so what do we have here? Right, so we covered the theory of a law of large numbers and CLT. We talked about weak law of large numbers and that there's multiple formulations of LLN. Then we spoke about CLT, central limit theorem, and looked at one particular formulation. By the way, here I didn't maybe emphasize it, but here we have in CLT the requirement that variance is finite, right? So in LLN and Hinchin formulation, we didn't say anything about the variance. It wasn't important, but in CLT, we do say something about the variance, and in particular, we say that it's finite, right? So as I said, there's different formulations of both LLN and CLT, and they allow them to be used in different situations where variance is finite, where it's not finite, and all that stuff. Right, so we spoke about implications, and I said I'm going to show you the demo, but before we go to demo, I just wanted to maybe jump into the next slide and say the following. There are multivariate formulations of both LLN and CLT. So here I'm just showing you a couple of points on multivariate CLT, right? So again, what CLT says, it says that if you have a sum of large number of random variables, then that sum will be a random variable itself, and it will come from from normal distribution, right? What multivariate version says, it talks about the sums of vectors of random variables, which we called random vectors. Right, so how do we do that? Well, we create this stacked matrix X as usual, right, with columns which for every variable and rows for each observation. So imagine if you have let's say k random variables, you'll have k columns. And then you will have observations in rows. So what happens is that the theorem looks almost exactly like a univariate one, but here instead of using mu as a scalar, we use mu random vector. It's a random vector. It's a vector of means of random variables, right? And then instead of using sigma as a variance of random variables, now we use this big sigma, which is a variance covariance matrix of the random vectors. All right, so that is the difference. It takes a little bit of getting used to, but maybe we'll look at some example later. But you know, the beauty of math is that the formula looks almost exactly the same, right? And implications are again similar. So now let's jump into the video, into our demo, right? So to remind you, right? So what we're talking about in CLT, we are talking about random numbers xy, let's say n of them, and then we are looking at the average of n random numbers, and we are saying that this average will come from normal distribution. Well, we'll have to scale it by square root of n, so we'll get the average multiplied by square root of n, average minus true one, and this will be normal distribution. So in my demo I will know what is mu. Obviously in practical situation you don't know what's mu, you only know this variable, the average, right? But you know something about the normal distribution, so now you can make inference, you can make some hypothesis about the true mean. But in my demo I know the true mean, so I'm going to show you that if I get the average and then subtract true mean, because I'm going to generate these random variables around true mean, and so but each variable will be different, it won't be at the mean. So I'll take the average, and then I subtract true mean and multiply the square root of n, meaning that I will try different number of n in this average, right? So I will get just one number, and then 2, 3, 4, and so on, and I will observe how when I'm increasing n, meaning the number of variables in the sum, in the average, I will see that when I'm increasing n, this whole left hand side will start looking more and more like a normal distribution. So let's just jump into my example. In the slides, obviously you will just pick up my URL to this example. You will be able to run it yourself in Google Colab environment as usual. Right? So let's correct it. We are in 2021 now, right? So, and I made some changes today, just today, right? So you will come to this Google Colab, and the very first code block, or cell they call it in Jupyter lingo, it's just a histogram plotting routine. So we'll just run it. It doesn't produce anything, right? But now we're going to look at this. So what am I doing here? I'm doing here, as I said, I am generating, if you look at this line, right, I am generating the random variables from uniform distribution. And you know, uniform distribution, it has equal probabilities of any number between, let's say, 0 and 1. Right, so I get the numbers between 0 and 1, and you see here what I'm doing is like I'm centering it, right? So if I get the numbers between 0 and 1 and subtract 0.5, then the mean will be 0. So my mean now is 0. But my random numbers range is now from minus 0.5 to plus 0.5. And then I'll multiply it by 2, so the numbers become between minus 1 and 1. But with equal probabilities, and that's exactly what I'm seeing on the west plot, right? So here it says n equals 1. So I'm getting n exactly one number, and there's 10,000 of them, right? So I get 10,000 numbers and just show them on this plot, on this histogram, and you see, well, it's it varies obviously, but it looks like a uniform distribution, right? So they are uniformly equally probable. Now, the next thing I'm going to do is the following. Now, I get two numbers and get the average of the two numbers. Simply, I'll get the average of two numbers. So when I do that, my next plot comes. And remember, in the beginning of this module, I said the sum of two numbers, or the PDF of the sum of two numbers, will not be equal to the sums of PDFs. So if you look at the first histogram, it's basically a PDF, right? This is a PDF of your one uniform number. And now look at what's going on the right-hand side. On the right-hand side is the average of two numbers from uniform, and we see that the PDF definitely is not the sum of the PDFs of each random variable. Otherwise, it would have been a rectangle like this, right? It's not. It's some kind of a triangle. Right, so this is a histogram of the average of two numbers. Now let's keep increasing. So I get 3, 4, 5 numbers and so on. And you see, while I'm increasing the number of variables in my average, my histogram looks more and more like this beautiful bell-shaped curve. Right, so it becomes, well, I don't have a proof here, obviously, because I would have to show that it actually is normal. There's a lot of bell-shaped distributions, but I guess what I'm trying to show you here is that when I increase the number, the number of variables which I'm averaging, they look more and more like some sort of bell-shaped distribution. And since you know central limit theorem, you can guess it's normal. And it is normal distribution, right? So you can, as an exercise for yourself, if you work with this Collaborate notebook, what you could do, you could actually study the properties of this distribution. For instance, look at kurtosis. is it equal to 3? Normal distribution will have a kurtosis equal to 3. So what are these numbers? This distribution doesn't have kurtosis equal to 3 or close to it, and so on, right? So you can study and convince yourself, oh yeah, it actually is becoming normal, but that's what's going on. Now I thought I'll show you an example with even more extreme case where, see here, it was a uniform distribution, but now I'm using Bernoulli. So think about this. Bernoulli distribution looks nothing like normal at all, right? It's just two numbers. It's like barbell type of distribution, minus whatever, 0.5 plus 0.5, right? But what I'm doing here is the following. I'm now adding this Bernoulli distribution. So if you have one number, okay, it's Bernoulli. But then if you have two numbers, look, it starts looking interesting, right? 3, 4, 5, and so on. So when you have 100 Bernoullis, ultimately abnormal, like absolutely not normal looking distributions. So when I'm using 100 of them, okay, look, it's becoming more and more like normal. So it actually is becoming a binomial distribution, right? If you know binomial. But binomial tends to become I mean, in the limit, it becomes like normal. Normal is a good approximation of binomial distribution. Anyhow, even the very extremely not normal looking distributions, right, when you add them, when you add a bunch of numbers or when you average a larger and larger sample, it starts looking more and more like normal distribution. That's how CLT works. And the final third part of this demo, I call it how CLT doesn't work. Let's look at something else here, right? So something else here is, okay, we have this bell-shaped distribution, which actually kind of looks more normal, right, than either Bernoulli or uniform. So we started with distribution, which is already bell-shaped, beautiful, right? So it seems like if we keep averaging larger and larger number of these bell-shaped distributions, we should get even closer to normal faster. But look at what's going on here. So we got 100 of them, and it looks nothing like a bell-shaped, like normal distribution, right? Something's going on here. And what's going on here is the following. Once you look at what I'm doing here in my code, I'm basically using something called Cauchy distribution. Cauchy distribution is kind of a student distribution, right? So if you have a student t distribution and increase degrees of freedom infinitely, it becomes normal. Right, so student t distribution with infinite number of degrees of freedom is normal. It's a limiting case. But if you decrease the number of the degrees of freedom of student t distribution, at some point it will become a Cauchy distribution. And Cauchy distribution, look it up, at which setting of degrees of freedom student t becomes Cauchy, right? But the Cauchy distribution is the one where not only the variance is not defined, but the mean is not defined either. It doesn't have a defined, well-defined mean. Okay, it looks like it's a bell shape, so mean must be 0. Well, mathematically, it's like, I'm not going to get into there, but basically mathematically, mean is not defined for this function, although it's symmetric and it seems like it should be 0. Well, median is. Median, of course, is 0, and that's a very important notion, and I'll talk about it in a second. So because the variance and the mean are not defined, CLT does not apply, and not only it does not apply, it actually doesn't work. We see it doesn't, the sum of Cauchys is not normal, and we will learn later in the course that Cauchy belongs to, like normal distribution actually, Cauchy belongs to the family of distributions called stable. So if you add two stable distributions, you get stable back. So if you add two Cauchys, you get Cauchy back. Right? So you don't get normal. That's why it doesn't converge to normal. So like typical CLT will not work for Cauchy distribution, but as I said, what's interesting is although it does not have well mathematically defined mean and variance, it does have defined median. Right, so it still has a median. That's interesting. So if you are running Monte Carlo and somehow you're using Cauchy somewhere in your Monte Carlo scenarios, you will run into this problem where your mean will not be converging to anything. It will not be converging. Your variance will not be squeezing and so on. But interestingly, as I said, median does exist, right? So that was my demo.